Today we are the group 2 of MA3C tackling the topic combustion mechanism. So an overview of the topic, next slide please. Okay. First one, we have the gas burners. Dito sa gas burners, meron tayong residential gas burners, industrial gas burners, and utility gas burners. The second one will be the liquid fuel reaction chambers or andito naman ang pag-uusapan dito is yung mga spark ignition engine and compression ignition engine. And lastly, ang solid fuel combustion chambers. Ang pag-uusapan naman dito is yung types ng combustion chambers, different types of combustion chambers, and yung boiler efficiency. Next slide po for the intro. So, introduction po muna tayo sa topic. So, dito sa topic natin na combustion mechanism, pag-uusapan natin dito is yung efficiency ng combustion. So, kapag sinabi nating efficiency ng combustion, hindi lang tayo tumutukoy dun sa combustion ng combination ng fuel and air, but kung paano natin siya kino-combine or mini-mix sa ating system. And ginagawa natin yon gamit yung mga combustion chambers. Combustion chambers are the mechanisms to properly mix the reactants and start the combustion. So, ang combustion chambers natin, sila yung nagmi-mix and sila din yung nagbibigay ng heat sa ating mga fuel. And sa ano natin, may iba-iba tayong fuel, types of fuel. Meron tayong gaseous fuel, liquid fuel, and solid fuel. So, lahat sila may different types of chambers na ginagamit. So, sa gas burners, sa gaseous fuel, meron tayong gas burners, which is usually ginagamit natin sa mga cooking, sa mga gas stoves, gano'n. Dahil sa mga gumagamit tayong mga LPG and industrial heating. Mamaya pag-uusapan. And next is sa liquid fuel natin, meron tayong mga ginagamit natin siya sa mga automobiles and engines ng mga sasakyan. Doon natin siya madalas ginagamit sa mga oils. And for the solid fuels naman, ginagamit siya usually for power generation. Kasi ang mga power plants natin usually ang gamit nila is tawag dito, ang main fuel na madalas gamit is coal. So, solid siya. Next slide po natin, sisimulan po natin siya sa gas burners. Ang gas burners ay gumagamit ng gaseous fuel. And alam naman po natin na ang gaseous fuel is unang-una, madali po siyang gamitin kasi madali siyang i-mix as well as madali siyang mag-combust. So, madalas po siyang ginagamit sa mga small scale combustion kasi mahirap siyang gamitin kapag large scale na yung gagamitin natin siya. And malaki-laki yung gagamitin nating gaseous fuel for that. And mahal siya kung ikukumpara sa iba since mahirap i-store and i-handle ang mga gaseous elements natin like air, hydrogen, mga gano'n. Since konting singaw lang or impact sa container nito is puwede na siyang mag-combust agad kasi mabilis nga siyang maghalo sa air which is kailangan niya sa combustion. So, unang types ng gas burners, next slide please, is yung tinatawag nating residential gas burners or yung mga ginagamit natin sa pagluluto, yun yun. So, meron tayo ditong 3 parts ng residential gas burners, ang inlet, mixing tube, and burner head. So, simulan natin dito sa may inlet port. Ang inlet port allows fuel and air to enter the burner. The gas affects the surrounding air, making it enter the port. So, ang sinasabi lang dito, ang inlet port is ito yung kumukuha nung gaseous fuel natin from the container. So, dito dumadaan yung gaseous fuel as well yung mga air natin since kinukuha niya na rin yung air natin kinukuha nung gaseous fuel yung air sa paligid niya. So, dun siya papasok. Next part natin dito is yung, pabalik ko na, yan. Next part is yung sa mixing tube. Ang mixing tube is nahahati natin siya sa dalawang part, isang throat and isang diffuser. So, yung throat natin, pa-next slide para sa definition. Ang throat natin is, nandito yung, highest point or highest pressure point ng mga fuel and air natin since, from small area siya. So, alam natin na kapag maliit yung area is mataas yung pressure. So, habang lumalaki yun, pumupunta siya sa diffuser, nagde-decrease naman yung pressure and ang velocity ng mga air and gaseous fuel natin is bumibilis. So, mas nagmi-mix siya sa ating mixing tube. Then, lastly is yung burner head, dito nakadikit yung mga port load natin na tinatawag. Ang port load is nandito na yung byproduct nating apoy sa mga gas stove natin. So, ang port load is usually in terms siya ng fuel flow rate per unit area. So, typical port load natin is 10 watts per millimeter squared and 50% primary aeration. So, sinasabi lang dito na ah, nakakakuha tayo sa isang port load meron tayong 10 watts ng flow ng energy or yun, fuel. And sinasabi din dito na it is advisable that the gaseous fuel should be burned close to stoichiometric combustion for better efficiency. The use of fan will greatly help to force air in pre-mixing of fuel and air, which allows the air to burn the fuel completely. So dito sinasabi na mas mas maganda or mas efficient yung burner natin if nabu-burn natin yung mga yung pinaka-fuel natin na gas, enclosed sa stoichiometric combustion niya. So, minsan gumagamit dito ng mga fan para mas tumaas pa yung mixing rate nung air tsaka nung fuel. So, tulad nga ng sinasabi natin kanina na kailangan yung combustion natin is not just about the combination of fuel and air, but also kung paano natin siya mini-mix para ma-attain natin yung efficient combustion na tinatawag. So, next po.
Next, industrial gas burners. These type of burners are used for heating applications, usually for manufacturing purposes. In this case, the gas temperature, heat transfer, and the flame shape should be considered. There are two types of configurations for this type of burner: a single nozzle and a two-stage nozzle. First, the single-stage nozzle. It uses the refractory nozzle to stabilize the shape of the flame. However, re-radiating heat from the flame causes it to reach the peak temperature and produce large amount of nitrous oxides. While using the next configuration, two-stage nozzle avoid these problems. Because in two-stage nozzle, the primary mixture can be a rich type while the secondary air can make the mixture a linear one. Thus, the peak temperature is avoided. Below is the figure showing a two-stage nozzle. Next is a ceramic fiber burner. This is an interesting concept when it comes to industrial gas burners. This burner uses a porous matrix of ceramic and metallic fibers formed into a cylindrical tube. The low conductivity of the fiber allows the burner to operate safely without worrying about flashbacks and limit the nitrous oxide emission as low as 15 parts per million. This type of burner usually has a heat at the rate of 800 kilowatts per square meter and mostly through radiation. Below is a figure showing the cross section of a fiber matrix burner. Next type is utility gas burners. These burners are used for electrical utilities and heating boilers with high efficiency and low emissions. In this type of burners, flue gas recirculation is common. The flue gas comes in contact with the fresh air so that the flame temperature is reduced, however, causing the flame to be less stable. And in order to make the flame stable, swirl is introduced. Swirl is a rotating flow around the central axis of the nozzle and is imparted by veins in the airflow passage. Below is a figure showing the effects of swirl in the shape of the flame or on the flame type. The first part shows only external recirculation and no swirl. The flame is in long jet in shape. Next, the, the two other figure shows medium to high swirl. It creates internal recirculation where the flue gas is mixed in high volume but still keeps the flame in shape in stable shape. Next is the efficiency of the chamber. It is an important consideration for the combustion chamber, and to have a basis of the system, the figure below shows a simplified schematic diagram of a gas-fired furnace. Next is the heat output formula. The basis of the equation is the heat from the reactants should be equal to the heat of the products, heat losses, and the useful heat output. Without creating the combustion formula, the number of moles of the products to the number of fuel can be determined with the use of this formula below, wherein Nc is the number of the mole of carbon in the fuel. Next is for the energy used to run the blower. It is equals to the volume flow rate of air times the change in pressure and over the efficiency of the blower. Next, for the efficiency of the boiler or furnace is equals to the heat output minus the energy used to run the blower over the mass of the fuel times the high heating value. Lastly, for the combustion chamber to be more efficient, the following measures should be kept in mind. First, decreasing the temperature for the exhaust products. Second, reducing the excess air, which will reduce the moles of products per mole of fuel and reduce the blower power. Third, reducing the extraneous heat loss. And lastly, reducing the blower power requirements.
For sample problem number 1, sulfur is burned with oxygen to form sulfur dioxide. The minimum mass of oxygen required and the mass of sulfur dioxide in the products are to be determined when 1 kilogram of sulfur is burned. So the properties given are 32.06 kilogram per kilomole for sulfur and 32 kg per kilomole for oxygen. So our first analysis is the given chemical reaction is sulfur plus oxygen, which is our reactants, yields to sulfur dioxide, which is SO2, which is our product. Hence, 1 kilomole of oxygen is required to burn 1 kilomole of sulfur, which produces 1 kilomole of sulfur dioxide whose molecular weight is. So, molecular weight of sulfur dioxide is equals to the molecular weight of sulfur plus molecular weight of oxygen is equals to 32.06 plus 32 kilogram per kilomole gives us 64.06 kilogram per kilomole. Then, for the mass of oxygen divided by mass of sulfur is equals to the given mass of oxygen times molecular weight of oxygen divided by the given mass of the sulfur times molecular weight of sulfur is equals to 1 kilomole times 32 kilogram per kilomole divided by 1 kilomole times 32.06 kilogram per kilomole will give us 0.998 kilogram O2 per kilogram S, which is oxygen and sulfur. Next is the mass of sulfur dioxide all over the mass of sulfur. It is equal to given mass of sulfur dioxide times the molecular weight of sulfur dioxide divided by the given mass of sulfur and then the molecular weight of sulfur. It will give us 1 kilomole times 64.06 kilogram per kilomole mole divided by 1 kilomole times 32.06 kilogram per kilomole. This will give us 1.998 kilogram sulfur dioxide per kilogram sulfur. So that is the answer for the sample problem number 1.
For sample problem 2, an atmospheric burner with a capacity of 20,000 British thermal unit per hour or BTU per hour is to be designed for a water heater. It is to be operable on either 1025 BTU natural gas or 550 BTU manufactured gas with proper orifice. The gravity of both gases is approximately zero point 0.6 with a given percentage of primary air 45%. Now, determine the maximum port velocity, the weight ratio of the burner mixture to fuel. Now, for the solution, we'll have to use the given formula of the maximum port velocity, which is equals to 7.25 minus 5.2 multiplied by percentage of primary air over 100. And the given percentage of primary air is 45%. The answer for maximum port velocity is 4.91. Now for letter B, the weight ratio of burner mixture to fuel, we'll have to use first, or we'll have to determine first the minimum line pressure for natural gas, which is based on the theoretical cubic feet air over cubic feet gas, which is equals to BTU over cubic feet divided by 96 minus 1, which is 9.7. Now, for the weight ratio, we'll have to multiply the gravity of both gases. 0. 0.6 plus 9.7 multiplied by 0.45 over the gravity of the fuel or the gravity of gases 0. 0.6, which is equals to 8.3.
For the second part of our presentation, we have liquid fuel reaction chambers. So, liquid fuels are mostly used for internal combustion engines, engines used in the likes of automobiles and small utility engines. For this part, we will cover two topics mainly: ignition engine and compressed ignition engine. In addition, factors affecting the design and combustion performance will also be covered. So, meron na tayong naging subject na internal combustion engine, and we were all familiarized with the works and the computations regarding the performance of the internal combustion engine, both spark ignition and compressed ignition. Next slide po, please. For spark ignition engine, due to its property of rapid vaporization of gasoline and mixing with air prior to combustion, this engine is also known as a premix charge engine. Internal combustion engines consist of multiple piston cylinders with intake and exhaust valves and spark plug. The combustion of the mixture in the combustion chamber will increase the pressure in the chamber and push the piston head downward. As the piston head moves, it will cause the connecting rod to rotate and so the drive shaft, thus converting the heat from combustion to mechanical work. Proceeding, combustion occurs in four phases: spark ignition, early flame development, flame propagation, and flame termination. So, if hindi po kayo familiar sa flame propagation means yung spread po ng flame. So, referring to the graph below, point A is where the ignition is in point A to B, distance from A to B is not to be the ignition. Point B to C is the propagation phase, and then point C to D is the afterburning or flame termination phase. Next slide po. So the ideal combustion process starts before the compression stroke ends and stops when the peak pressure is reached. As can be seen from the graph or the effect of timing to the cylinder pressure, uh, the ignition is introduced before the mixture is fully compressed. This is necessary to be able to reach the maximum brake torque. Uh, the figure 2 effect of timing to the cylinder pressure shows the effect of spark timing to the peak pressure and the maximum brake torque. If the timing is pretty advanced, this will result to a very high pressure inside the chamber, which may be beyond the design pressure of the chamber. If the timing is introduced the compression ends, known as ignition retardation, the peak pressure will be less and will not produce optimal torque. This will also result to short combustion inside the chamber and will yield more unburned mixture. The optimal timing depends on the flame development and propagation, length of the flame travel path across the combustion chamber, and the flame termination process after it reaches the wall. So, as we can see, the maximum brake torque is produced if the timing is 30 degrees relative to the top center crank position. So, as mentioned before, advanced timing results to very high pressure na pwedeng masira yung engine dahil sa too much pressure. And pag timing naman is masyadong late, yung mapoproduce niyang pressure will be lesser and hindi siya makakapag-produce ng enough torque to power the crank. And then, next graph is showing the effect of timing. Oh, sorry. The cylinder pressure as a function of crank angle. Cycle to cycle maximum pressure is different at each cylinder due to the difference in flame growth inside the combustion chamber at each cylinder. Depends on the local mixture, motion, and composition. Although the amount of mixture is at each cylinder, its composition may vary a little due to the mixing methods and timing. Next po, for flame propagation.
Flame propagation. It is the spread of a flame in the combustible environment outward from the point at which the combustion started. Two factors affect the flame propagation. Reaction rate, where the flame causes the unburned mixture to combust and transposition. Rate, where the movement of the flame causes pressure differential between the burning gases and unburned gases. Flame propagation is highly reliant on the condition affecting flame travel, on the quantity of charge present in the chamber and the turbulence, because the peak pressure is dependent on flame speed, is reliant on the spread of flame. Flame propagation is too brief, further poor combustion and lengthy the speed, and at if a flame eats unburned mixture. The interplay of the charged object and the turbulence is what mixture and unburned mixture, boosting the velocity of reaction as a result of contact. Higher flame is produced by spinning of the tiny particles. When the incoming mixture develops momentum, turbulence is produced. Fuel ratio also affect the flame speed. If the mixture is rich, then combustion will be shorter. Learner mixture will take more time to combust, since the fuel particles are less in this case. However, having a rich mixture beyond will resort to incomplete combustion. Knocking in CI engine, sharp sound caused by premature combustion of the part compressed air fuel in the cylinder. In a properly functioning engine, the charge burns with the flame front progressing smoothly from the point of ignition across the combustion chamber. The CI engine also experiences knocking, which happen during the injection phase. Only a tiny number of droplets will ignite at a time if the injection rate is maintained, resulting in a gradual rise in temperature and pressure inside the chamber. Closer to the TDC, if additional fuel is permitted to be pumped into a combustion chamber before it begins to burn, there is a sudden rise in the pressure that results in jamming pressure against the piston and rough engine running. The rate of pressure increase will quickly if a longer ignition delay is permitted, leading to high pressure differentials and intense gas vibration that can cause audible knock.
Abnormal combustion. Pressure inside the combustion chamber also changes due to the amount of unburned and burned mixture inside the chamber. Some cylinders will have more unburned mixture than the others, affecting the combustion inside the chamber. Abnormal combustion is also the process where the fuel burns not only by spark but also by self-ignition process, where a number of waves of flames are produced from different parts of cylinder. Having unburned mixture inside the chamber is common, however, how and when it burns will cause abnormal combustion. Next. Knock ignition. Knock is the term used to describe pinging noise emitted from SI engine undergoing abnormal combustion. When the spark when the spark plug fires the entire fuel air mix and it doesn't ignite at the same instant, the flame is spreads outwards from the spark plug. Knock often occurs when something causes some of the mixture to ignite before the flame front has reached it. And this is basically an uncontrolled large amount of mixture. Dito sa graph na to, makikita natin yung pressure na meron sa engine sa tuwing yung knock ay nangyayari. Next. Uh, Ito naman yung pictures ng damage ng engine from severe knock. Next. Surface ignition. Surface ignition is ignition of fuel air charged by overheated valves or spark plugs. By glowing combustion chamber deposits or by any other hotspot in the engine combustion chamber. It is the initiation of flame front by a hard surface other than the spark plug. Mostly surface ignition is due to carbon deposits. Causes of abnormal combustion and SI engine is, yung una is yung fuel condition including quality, quantity, and other attributes. Engine scanting or yung geometrical size ng engine na kung saan meron siyang condition of piston, piston rings, bearing condition, lubrication, tsaka spark plug. Pangatlo ay yung engine coiling efficiency at tsaka yung pang-apat yung vibration. Next.
Next po is yung compression ignition engine. So for this part, in compression ignition engines, combustion occurs when the mixture of air and fuel reaches its ignition temperature due to the increase in pressure inside the chamber. So yung compression ignition engines ay most commonly known as yung sa mga ginagamit na engines for diesel fuel. Na-discuss na rin natin to dun sa ICE nat or dun sa internal combustion engine subject natin, and kinupit din natin yung mga and the work na napoproduce ng type ng engine na yan. Similar siya sa SI, yun nga lang, ang difference niya is wala siyang spark na kailangan para mag-combust. And instead, ang kailangan niya lang is tumaas yung pressure inside dun sa chamber and tataas na yung temperature which substitutes dun sa spark na yun para mag-cause ng heat and then magkakombust na yung fuel sa loob ng chamber. So, for the stages of combustion in a CA engine, presented siya below. So, sa figure 4, stages of combustion in a CA engine. So, basically, may apat siyang stages. One is the ignition delay period. Second is the period of rapid combustion. Third is a period of controlled combustion. And then lastly, period of afterburn. So first stage is ignition delay period. Known as the preparatory phase, this is where the fuel is injected in the combustion chamber. Two parts of ignition delay is physical delay and chemical delay. So uh, yung physical delay is where the fuel is atomized and vaporized and mixed with air to reach the self-ignition temperature. So, sa chemical delay naman is when chemical reaction starts, chemical delay happens. In this case, the ignition starts. So, the fuel is injected at 20 degrees of the TDC or yung crank. During this delay period, the air and fuel mixture spreads throughout the combustion chamber. The delay period is a great influence in the engine design and performance. The combustion rate and knocking is affected by the delay period. The factors affecting yung delay period na to is such as compression ratio, intake temperature, jacket water temperature, fuel temperature, and etc. So next po is yung period of rapid combustion, also known as the period of uncontrolled combustion, and where there is a rapid rise in pressure experienced. This period is from the period of the start of combustion until the maximum pressure in the chamber is reached. Due to the delay period, this will result to a higher rapid rise because most of the fuel is already oxidized. Next po, period of controlled combustion. At constant temperature, the fuel and air is continually injected to the system, thus increasing the temperature inside the chamber. This is the second stage of combustion, and any unburned mixture during the first stage is burnt in this stage. This period ends when the maximum cycle temperature is reached. Lastly po is yung period of afterburning. Despite the slow decrease in pressure and temperature at this period, there is still left enough for unburnt and partially burnt fuel particles left in the chamber to burn as soon as it comes into contact with oxygen. So, ang sinasabi lang sa afterburning is yung mga fuel na naiwan dun sa chamber na hindi na oxidize or nag-combust is magko-combust siya uh, as the pressure and temperature decreases sa period na to. Next po.
Knocking in CI engines. Knocking occurs in diesel engine due to the delay period. This occurs due to the additional amount of fuel is injected into the combustion chamber when the first amount of fuel injected into the chamber that has a delay period pass for the preparation of the flame reaction. In this table, it shows the comparison of the different characteristics to reduce the knock on SI and CI engine. Next, combustion chamber for CI engines. Combustion chamber is a part of the internal combustion engine in which the combustion of the air-fuel mixture takes place. Uh, this is an this is an enclosed cylinder. A combustion chamber is also known as a combustor. The combustion chambers are most commonly used in the engines of cars, ships, airplanes, etc. And if you have an automobile or a car, you can easily find it here. There are two types of combustion chambers, where the first one is direct injection type. And in this type, the combustion chamber is in one main cylinder, and all the fuel is injected in this space. Uh, this is also called open combustion chambers. The entire combustion space lies in the main cylinder, and the fuel is injected into this volume. The next one is the indirect injection, or IDI type. In this type of combustion, chambers or combustion space is divided into two parts, one in the cylinder head and the other in the main cylinder. Fuel is generally injected in the part which lies in cylinder head. Next. And in this graph, makikita natin yung uh, advantages and disadvantages ng direct injection at indirect injection. Where the advantages of direct injection are minimum heat loss during compression, fine automation because of multi-hole nozzle, at kanyang drawbacks are requires high fuel injection pressure and necessity of accurate metering of fuel. While the advantages of indirect injection are injection pressure required is low and direction of spraying of fuel is not important. At ang kanyang drawbacks are poor cold starting performance and specific fuel consumption is high. Next.
And for the third part of our presentation, we have solid fuel reaction chambers. Solid fuel, unlike the other two fuel types, has to undergo pretreatment prior to its use. This is primarily due to the high moisture content of the solid fuel. Ang solid fuel combustion ay binubuo ng drying, evolution, and burning of volatiles and solid phase combustion. Ang biocarb combustion ay nabubuo sa pamamagitan ng fragmentation at pagtunaw or melting. At bumubuo ito ng medyo malalaking particles na nagpo-form ng bottom ash and fly ash. Next. Drying. Free moisture can be removed through the process of drying that can be through natural or mechanical method. The acceptable moisture content is at least 30% before it is used. Aside from drying, some solid fuels need to be resized prior to feeding. One is that it may fit the chamber and to hasten the flame spread, especially for biomass fuel. And next is the volatilization. The volatilization is the next stage to combustion. In this stage, after the moisture of the fuel is removed, the volatiles are released through the pores of the fuel. In the volatilization, the oxygen cannot penetrate the inside of the fuel. Thus, combustion occurs without oxygen, which, which is also known as pyrolysis. Ignition of the fuel may occur when the volatiles ignite in the boundary layer around the particle or fixed carbon found on the surface of the fuel. The ignition time of the solid fuel is depends on the particle size and thermal diffusivity, heating rate, and pyrolysis rate. If the combustion is to continue until the car is burned out, then the combustion process is complete. The remaining particle after the combustion is ash. The mineral matter does not burn. Ash remains softer when the fuel is burned in low temperature. But for high temperature burning, the ash form is glassy spear known as xenosphere. The formation of ash can cause slagging and fouling of it transfer surface. Next.
Types of combustion chamber. Cook stove. Solid fuel is first used for space heating and for cooking. The advantage of cook stove is that it can build easily and can use wide range of fuel. The image shows that with the aid of stone as a support for the pot, and the space below the pot is where the fuel is placed. This is known as an open burning, and although it is easy to build, it is highly inefficient. This is due to the most of the heat produced due to combustion is not transferred to the pot, but to the surrounding air. It is also prone to a wastage of fuel, because as more fuel is used, the bigger the flame, which aids in hastening the cooking process. But most of the heat is again not utilized effectively. Next. The first image shows that the residential space heating. This is the improved cook stove includes the insulation of the sides of the chamber. For this will reduce the heat losses, and the inclusion of the chimney aids in the airflow direction. The third image shows that the rocket stove. It is also the improves of a cook stove. Next. Next slide, please. Great burning system. For industrial application and when crushed solid fuel is used, great burning system are used. There are two burning system schematic types of grate that can be used. One is a conveyor type as shown in the first image, and the vibrating type second image. In this burning system, the fuel is placed on a platform or grate, and the airflow is from the below. The fuel falls through the grate with the aid of gravity or is spread when the fuel is flung across the grate. In grate burning system, the ignition starts from the top of the fuel due to its exposure to the radiation of the boiler and propagates downward in the bed against the airflow. Next page, please. Grate burning system. For industrial application and when crushed solid fuel is used, grate, grate burning systems are used. The slide shows the two types of grate, grate burning system. The vibrating type has the grate slanted by 6 degrees and intermittently vibrates at a rate of 6 cycles for 2 seconds, then for 2 minutes. The advantages of the vibrating grate is it is fewer moving parts, thus requiring less maintenance. Due to the vibration, the fuel bed is more uniform and the airflow is uniform all throughout. Next, please.
Pulverized coal burning systems. Pulverized coal is burned using the suspension burning method. In this uh, combustion system, the pulverized coal particles are blown through burner nozzles. In this system, the coal is pulverized to phase powder, and that is done to ensure rapid combustion. Phase powder coal is created with the aid of ball mills that grinds down the coal, and the raw coal is mixed with the air and is piped to the burners, and exits the burner nozzle at 75 degrees Celsius and 25 meter per second. The primary air constitutes the 20% of the air required combustion air. The rest of the air needed for the combustion is supplied by the preheated secondary air coming from the wind box. The ignition occurs and flame is stable due to preheated secondary air and the swirl of the secondary air. Also, the volatility content of the fuel is at least 20% to maintain the stability. In this type of system, the location of the fuel and air nozzles is an important consideration in the design. There are two options for the firing method. Dry bottom, where the temperature inside do not cause the ash to agglomerate into molten globules and does not fall at the bottom of the furnace, and wet bottom firing, where the high temperature is necessary to add in the ash melting. In wet bottom firing, the nozzles are located near the bottom of the furnace floor. Aside from the placement of nozzles, the wet bottom systems are prone to slagging and corrosion and have higher nitrous oxide emissions, while dry bottom firing have higher uncontrolled fly ash emissions. Uh, the different configuration for the dry bottom firing are: A is the horizontal, B opposed horizontal, C tangential, D opposed incline, E U single U flame, and last F is double U flame. The design of the furnace should ensure that the heat is transferred effectively from the combust materials to working fluid in the boiler. So in the image on the right side, they are the dry bottom furnace and burner configuration. Next is fluidized bed boilers. Fuel fluidized beds are usually used for crushed coal and sulfur capture is required. A fluidized bed is a bed of solid particles that are set into motion by blowing gas streams upward the bed. The difference from the suspension burning is that the speed of airflow is enough to suspend the particles, but that small that it would not be blown out of bed. So the freeboard is used to disengage the particles that are thrown up above the bed and to complete the combustion of volatiles and fine particles that were unburned in the bed. The schematic shows the bubbling fluidized bed. The other type is known as the circulating fluidized bed, where the part of the fuel is and the bed particles are entrained by high gas velocity and recirculated back into the lower part of the bed. The circulating fluidized beds were developed to overcome the carbon carryover of bubbling beds and facilitate uniform fuel feeding. So so this is the fluidized bed boilers. The other types of fuelized fluidized bed, the air bed, air fixed bed, air bubbling, Uh, oh, and circulating. The advantages of fluidized bed boilers over the fixed bed and pulverized fuel boilers are low, low uh, nitrogen oxide emissions due to relatively low bed temperature, have a good fuel flexibility, can burn wide range of solid fuel with varying ash and moisture content. Boiler efficiency. Combustion efficiency refers to the completeness of combustion, and it is uh it has a formula of um uh and it equals to Q minus W uh auxiliary power and over M M F times HV. So the auxiliary power is the power necessary to run the fans, pumps, and feeders. It is a typical in this system that the power produced is used to power the other components. Thus, the net useful output is considering the auxiliary power. Sample problem. A boiler generates 6,200 kilogram of steam per hour at 8 bar and 0.91 dry from feed water at 38 degrees Celsius of coal per hour having calorific value of 31,000 kilojoules per kilogram. Determine the efficiency. So the given is our MS is equal to 6,200 kilogram per hour. The pressure is 9 bar and the dry is 0.39. Then the initial uh, temperature is 38 degrees and um, our our MF is equal to 825 kilogram per hour and our CV is equal to 31,000 kilojoules per kilogram. Then the solution is efficiency equals output over input. The normal thermal efficiency equals coming heat coming out and over heat supplied. So N is equals to heat of steam over heat supplied. So our equation is Ms times Ms minus HF1 over MF times CV. So first we need to find H2 and that is equals to HF2 plus D2 times HFG2. From the steam table, we can get the HF2 and HFG2. They are 742.6 kilogram per kilojoules and the HFG2 is equals to 2029.5 kilojoules per kilogram. And our H2 is equals to uh, uh, HF2 plus ta- x2 times HFG2. So when we substitute the value, uh, we, we will have 742.6 plus 0.39 times 2029.5 and when we calculate it, it will be equal to 2630.035 at now at 38 degrees Celsius, HF1 is equal to 151.1 kilojoules per kilogram. And using our equation for efficiency, uh,
6,200 times 2,630.035 minus 151.1 over 825 times 31,000, we will get 0.599, or it is equal to 60% efficiency. So, uh, thank you for listening to our presentation, and um, that's all. Thank you.